Okay, so just want to remind you uh, of the total differential formula that we came up with last time. So first of all, if z is a function of f, it's a function of x and y, but let's say x is a function of t and y is another function of t, um, then z is really a function of t. Um, what we want is the derivative of z with respect to t. How does z change time? Okay, so recall the total differential. Dz is equal to fx dx plus fy dy. And just to remind you, dz is change on a tangent plane. So that's the change on a linear approximation f of xy. Okay, dx is just, the same as delta x. It's just the change in x, and dy is the same as delta y, change in y. But dz is only the change on the tangent plane. Delta z is the change on f of xy, on the surface itself, not the linear approximation. So let me make that note here, not the tangent. Okay. So delta z is approximately dz. And we could go ahead and say that this is fx delta x. Oops, let me, I got that backward. I meant to say that delta z is approximately dz. So that's fx delta x plus fy delta y. Okay, so that's just coming from the differential. Delta x and delta y are essentially the same thing as dx and dy. And so delta z is approximately fx times delta x plus fy times delta y. And over a time change of delta t, so let's say if this change in x and y corresponds to a change in t, which we'll call delta t, then delta z over delta t will be approximately fx delta x over delta t plus fy delta y over delta t. Okay, and as long as no denominators go to 0, so let's assume no, let's say nothing undefined. Occurs as delta t goes to 0, then this becomes the chain rule. So dz over dt equals fx dx over dt plus fy dy over dt. Just like that. Okay, any questions about that? And there's a similar chain rule for partial derivatives as well, which I'll show in a little bit. Let's do a quick example. So f of xy is equal to x squared plus 2x e to the y. And then let's go ahead and say that x is t squared and y is t to the third. Okay. Then, and of course, z is f of xy. Okay, so then dz over dt is an ordinary derivative because there's really only one independent variable here. With one independent variable, there is no partial derivative. It's just an ordinary derivative. And so the rule is fx dx over dt plus fy dy over dt. So we can kind of start punching stuff in here. So fx looks like it'll be 2x plus 2e to the y. And then that's times dx over dt. Up here, dx over dt is just 2t. So we'll multiply by 2t. And now plus fy, partial derivative with respect to y, I think, going up here, looks to me like the x squared will go to 0. And the derivative of 2x e to the y would just be 2x e to the y. And then times dy over dt, and of course, dy over dt would be 3t squared. Like that, so we'll multiply by 3t squared. Doesn't look bad, but there's too many variables here. And so I don't know, normally we like to clean this thing up and say, okay, well, 2x would be 2t squared plus 2e to the y, that's plus 2e to the t to the third times 2t plus 2x, that's 2. X is t squared. E to the y, that's e to the t to the third times 3t squared. Isn't that lovely? Now you can multiply this out if you like. It's not going to be good. So probably won't carry this out much more other than just to multiply everything out. So I think I get a 4t to the third plus 4t e to the t to the third. Okay. plus, it looks like a 6t to the 4th, e to the t to the 3rd, like that. Now, I have not really been checking backward for mistakes. I'm going to pull my chat window up. No big complaints, it looks like. Okay, looks pretty good to me. I don't see any mistakes. So there's a quick little example. I should make a note somewhere here and say the chain rule is mostly good for theoretical discussions. So you'll see me use the chain rule when we do a proof, and then you'll never see me do the chain rule again. So don't get too worked up about having to remember these formulas. They just aren't that useful. Okay. If somebody asked me to take a derivative, I guess I'll show an example of that, but okay, let's continue on. There's a higher dimensional chain rule in a sec. So let's continue with z as a function of x and y. But now x is a function of two independent variables, s and t. So now derivatives will be partial derivatives. And y is the same function of s and t. Okay, any questions? Then you can kind of look up above as guidance when I say dz over ds, but I'm going to say partial of z with respect to s. And I'm just using the chain rule up above here as guidance. Instead of taking a derivative with respect to t, I'll use an s. And instead of using d's, I'm going to use these symbols that are called nablas. So I'll have an fx partial of x with respect to s plus fy partial of y with respect to s, and partial of z with respect to t will be the same, fx times the partial of x with respect to t plus fy partial of y with respect to t. And again, I don't think I've ever used this outside of this section of the book. So we always cover this and we never use it, again, only for theoretical reasons. Okay, so maybe a quick example of that. Looking to see if anybody has questions. I don't see anything. Let me just double check here. Yes, I don't see any questions. I'm gonna keep going. Okay, so here's the next one. Suppose z equals f of xy. And now that's going to be 9 minus x squared minus y squared. Okay. And we're going to have x be a function r cos theta. So I'm just putting x and y into polar coordinates. So y is going to be r sine theta. Okay, so that's just sort of, all right, let's do a derivative with respect to r and theta. So we're just switching over to polar coordinates. So the partial of z with respect to r is going to be fx times the partial of x with respect to r plus fy times the partial of y with respect to r. Okay, and that's a lot of work to do something that's actually really simple. But we'll go with it. Fx is going to be negative 2x partial of x with respect to r. I wonder if somebody would say it. So the partial of x with respect to r, I think should just be cos theta, right? And then plus the partial of f with respect to y will be negative 2y times the partial of y with respect to r, which would be sine theta. Okay, so blech. If you want to simplify this, you would say negative 2, and then x is our cos theta. And then minus 2y. Oops,
We can't. Yeah, you have a frozen screen, Professor.
I have a frozen screen. I'm going to pause then.
Oh, I think it came back.
Yeah, that's just like when it gets overloaded. Sorry about that. So then I get the cos theta in here. And then minus 2, and y is r sine theta. And then times another sine theta. Okay, so what I see here is a negative 2r cos square theta minus 2r sine square theta, which of course is going to just be negative 2r. Okay. That's a lot of work to do something that's actually super simple, which I'll show in a second. Let's do the next partial. Well, why not just squeeze it in here? Notice that z is 9 minus x squared plus y squared. Because you know that x squared plus y squared is r squared. So z, if you were to find a formula for it, z is actually just 9 minus r squared. Okay, so clearly the partial of z with respect to r is the partial with respect to r of 9 minus r squared, which is clearly negative 2r. So did the chain rule make your life better or worse? This is just a direct computation here, where the other was chain rule. So again, I think you can easily see that the direct computation is much simpler. Chain rule is not always a good thing. Okay, let's see the next one. So the partial of z with respect to theta. Now I can see the answer. What's the answer going to be when you do the partial of z with respect to theta? You can just say it out loud. Look at it up here. Yep, 0 is the answer. We're going to do 0 the hard way. Ready? Partial of z with respect to theta. So this should be fx partial of x with respect to theta plus fy partial of y with respect to theta. So fx, as before, is negative 2x. Partial of x with respect to theta would be negative r sine theta. And then fy is negative 2y. And then the partial of y with respect to theta is r cos theta. Okay, then now you start doing your substitutions. The negatives cancel, you end up with 2x, which is r cos theta, times r sine theta, minus 2y, which is r sine theta, times r cos theta. And so I think what you've got is 2r squared cos theta sine theta minus 2r squared cos theta sine theta. And of course that's 0. So we knew it was going to be 0 because the partial of z with respect to theta is the partial with respect to theta of what we said z was, which is just 9 minus r squared, which is 0. So we knew that it was going to be 0 because of that. And the chain rule is not usually your friend. So don't think you're going to be using it constantly. Now we're doing 744. Okay, so any questions about all that? You can just say it out loud or type it in. All right, I don't see anything there. This is the craziest thing that comes up next. It's implicit differentiation. Using the chain rule. So the implicit differentiation is where you can't or you don't want to solve for y. And this is just for ordinary derivatives. So suppose y is a function of x. Maybe I want to say it this way, y is equal to y of x. So you know it's a function of x, and that's usually where we write that. But it's defined implicitly as a big F of x, y equals some constant. Okay. So here goes. Big F of x, y equals little space and a constant. What we want to know is what y prime is without solving for y. So what we're going to do is the derivative with respect to x on both sides. Okay, now on the left side, you're going to have to use a chain rule because you've got a function of two variables, and at least one of those variables is a function of another variable. So on the left side, you've got to do fx times dx over the variable you're taking a derivative with respect to, so that's dx also. So that's just going to be 1. Plus fy times the derivative of y with respect to x. So that's the chain rule. Okay, and of course, this is equal to the right side, which is 0. Okay, and we're trying to solve for dy over dx, so that's easy enough here. Of course, dx over dx that's just 1. So what you get is that fy dy over dx is negative fx. So dy over dx is negative fx over fy. And that right there is an explicit formula for implicit differentiation, which I just love saying because it's sort of oxymoronic. It's an oxymoron. Okay, so little example here. You've got x squared plus 3xy plus 5y squared equals 1. You don't want to solve that for y. Okay. Of course, you could do implicit differentiation the old way, but who wants to do that? We're going to call this big thing f of xy. And right off the bat, you know that y prime is negative fx over fy. Okay, so negative fx, this will be negative partial of f with respect to x. So that'll be 2x plus 3y over fy. Now you're taking the derivative of that big F with respect to y. So x squared goes to 0. Derivative of 3xy is 3x. And the derivative of 5y squared is 10y. That is implicit differentiation of the y. Okay, any questions? Now you can extend this. I'm looking for questions real quick here. I don't see anything. You could extend this to partial derivatives too. So for big F of x, y, z equals a constant where z is f of xy. I'll do z of xy again, sorry. Z is z of x, y implicitly. Then I'll just extend the logic here and say the partial of z with respect to x would be negative fx over fz. And partial of z with respect to y is negative fy over fz. Okay, so that's again kind of a clever thing. I don't know how helpful it is. It's a cute little trick, I think, is about all I get out of that. Okay, so let's just do a quick little sphere. Okay, so here comes for the sphere. And the sphere is x squared plus y squared plus z squared equals 14. Note that 1, 2, 3 is on the surface. Which is to say that 1 squared plus 2 squared plus 3 squared is exactly 14. Okay. So my big F of XYZ is this thing on the left. Yeah. And so the partial of Z with respect to X would be negative Fx over negative over positive, just negative Fx over Fz. So negative Fx would be negative 2x. Fz is 2z, so that's over 2z. So this is just negative x over z. Now if we evaluate this at the point 1, 2, 3, then you'd say it's negative x, which is 1, over z, which is 3. So that's basically the slope on that surface, the sphere, at the point 1, 2, 3, the slope in the x direction only. And then the partial of z with respect to y is negative fy over fz. Of course, this will be negative 2y over 2z, which is just negative y over z. And I want to get it again evaluated at the same point 1, 2, 3. So that's easy enough. Y is 2, so you're going to say negative 2/3. Okay, and then the tangent plane. So what is that? Just in case I wanted to do that. Just to remind you that the z is fx at x naught, y naught, times x minus x naught, plus fy at x naught, y naught, times y minus y naught, and then plus z naught. Okay. So the partial of z with respect to x, that's your fx. The partial of z with respect to y, that's your fy. So you can just write this down. Tangent plane is equal to fx, well that was negative 1/3, times x minus x naught, the x naught was 1. And then minus fy, that'll be negative 2/3, times y minus y naught is 2, plus z naught, that'll be 3. Okay, so the point of tangency is x naught, y naught, z naught.